Okay, so good afternoon, everybody, and welcome back to forensic biology. And today we're going to be talking about fire and forensic aspects of fire and explosion investigation. This is a really important topic, and it covers actually one of the most difficult crime situations of all, and that is the event of a devastating explosion or of a fire. The problem being that not only may this be a crime, but much of the evidence is likely to have been destroyed. This is an instance where the crime itself destroys the evidence of it. And under normal circumstances, in the cases of a fire or of an explosion, criminalists will immediately hand over to a fire and arson expert because it requires a real expertise to interpret what has happened at such a scene. Okay, so first of all, we realize, of course, that not all fires and not all explosions are of criminal origin. Nonetheless, in all of these instances, an arson investigator will do the investigation. And the definition of arson is the willful or malicious burning of property, not necessarily only buildings, but any of property in general, with criminal or fraudulent intent. And these become extremely difficult because in cases of arson, you can be relatively sure that the perpetrator has planned what they were doing, and they will have planned it in such a way that it leads to as few clues as possible, which might lead back to them. Second of all, a perpetrator in a murder or whatever is actually there at the scene of the crime. Very often, a perpetrator is not present anywhere near where a fire or explosion takes place. The event is deliberately delayed so that they can be well away from the scene when it occurs. And lastly, as we have mentioned already, the destruction that takes place is often extensive, and it may be so great that it will obscure the origin of the event. Okay, so at this point, if you have not done so already, please stop this video and go to this movie, The Point of Origin, which I want you to watch before we proceed, because it will give you a good idea about all of these aspects of the crime scene investigation, plus a few more things to think about. Okay, so please make sure you watch this and watch it before we proceed. I'm going to now proceed, so you can just do it whichever way you want. I emailed you the link to the movie in case you have difficulty linking from the PowerPoint. Okay, so, all right, so hopefully you've all watched that movie, and it will give you a good understanding about a lot of what we're going to talk about. And I will keep this class short, bearing in mind that you've spent some time watching that movie. And so the criminalist function at a crime scene like this actually becomes rather limited. The criminalist being the initial investigators, right? Or the people who normally would collect evidence at the crime scene. Nonetheless, criminalists will immediately gather evidence that is in any danger of being lost. Remember that this is one instance where the unreasonable search and seizure strictures are lifted. If a fire is busy raging, then the officials are authorized to gather evidence, even if no warrant or anything has been issued. The second thing is, after a fire has died down and everything, a criminalist may immediately try and collect samples of likely areas where fuel may have been spread as an accelerant. And they'll do that because the sooner that they do it, the richer the sources of unburned fuel will be. And whatever they collect is placed into metal canisters, sealed, so that all evaporation is contained within that canister, and the canister can then be sampled. They will do as much identification of that evidence as possible, but almost always will hand over to an experienced arson investigator who will determine, first of all, if it's arson or not, but in any case will determine the nature and the origins of the event, whether it's a fire or an explosion. The arson investigators really need careful and special training, and they also need a tremendous amount of experience in order to try and interpret the scene that they're looking at. So let's understand a little bit about fire and a little bit about explosion. We sort of have we think we have an instinctive understanding about what a fire is or what an explosion is, but actually it's a little bit more complicated when you look at the details. So first of all, both of these events, fire and explosion, occur because of the process of oxidation. And in this case, the oxidation is a somewhat wider term than chemically a wider term than we're going to use, but we're going to use oxidation in terms of oxygen being combined with other substances to produce a new set of compounds. That is what happens when you burn something. When you burn something, you take a rich source of carbon, of fuel, and you combine that fuel together with oxygen, and ultimately what you produce is carbon dioxide, water, and a lot of heat. That if this reaction takes place rapidly, then you will produce a lot of heat which will be felt in a very short time. If, on the other hand, the oxidation takes place over a very long time, over years, decades, hundreds of years, which some oxidation reactions will do, they still release heat, but it's released so slowly that it's imperceptible. So, for example, rusting, that's a good example. It's a form of oxidation. It does release heat itself, but the amount of heat it releases is generally imperceptible. But this whole class of reactions in chemistry, they are known as exothermic reactions. So they are releasing heat, but that heat that they release is very important because the amount of heat that they release may propagate the oxidation of unburned material near them. So what happens when a fire burns is, we have to struggle to get a fire to start, right? You've got to really work at it, get a small area of the fuel to start oxidizing. When we put a flame to it, we get it to go. And once it's going, then it begins to be self-propagating. Because as the oxidation of fuel takes place, it releases sufficient heat that it can set neighboring molecules alight, so to speak. Now, when we burn a fire, in actual fact, that oxidation process is controllable. It is relatively slow. That's how we can have a fire in front of us, add fuel when we want the fire to burn up a little bit. But the wood doesn't explode in your face when you light it. On the other hand, there are other substances which oxidize extremely rapidly once they get going, and release a huge amount of gas and heat in a very short time. And those are the substances which cause an explosion. So we're going to distinguish between this ordinary fire and then these explosive events that we would associate with a bomb or with an explosion of some sort. All right, so when we want to start a fire, then we have to add some heat. This is because all chemical reactions require of this kind require a certain input of energy in order to begin to combine the molecules, the carbon-rich molecules of the fuel, with oxygen to produce carbon dioxide. That in itself requires the input of energy at the very, very start. The amount of energy we've got to put in to get the substance to start burning is called the ignition temperature. And it varies from substance to substance. So once we get that going, then you can sit back and read a book or toast your feet or whatever, because the fire becomes self-propagating. As burning of wood takes place, for example, it is sufficiently hot that it sets off wood near it and gets that to start burning. That starts the unburned wood next to that burning, and on and on and on until the fuel is completely consumed. So when we burn something, it releases heat, and that we know in fire terms, we call that the heat of combustion. And generally in a fire, it is released relatively slowly. In an explosion, it is released extremely rapidly. So when the heat of combustion reaches the same temperature as the ignition temperature, that's when the fire becomes self-propagating. So we add a little bit of heat and get it burning, produces heat of combustion, and when the heat of combustion is equal to the ignition temperature of the fuel, it starts the fuel near it burning. It rolls on as a self-propagating chain reaction. But there's things that we need. There are things in all fire. There are things which are essential. This is not true for explosions. Okay, the same things are not necessarily required for an explosive mixture. But a fire, in order to initiate and to sustain it, it must first of all have sufficient fuel. The wood fire that you're toasting marshmallows on is not going to last forever. It's going to burn until such time as there's no wood left, there's no carbon left for it to consume. The second thing is a fire requires the presence of abundant oxygen. This process of combining carbon and oxygen together to ultimately form carbon dioxide consumes 2 molecules of oxygen for every molecule of carbon. There must be an abundant source of oxygen present, or the fire stops. Combustion will end. And we have already said, we need enough heat to start the reaction. And when the reaction begins, then the fuel when it burns, has to be generating enough heat that it can sustain the reaction, propagate it to the rest of the fuel. Those are the 3 things that we're going to require. Really important is when we're talking about arson, because very frequently, one of those things actually ends up being missing. Or very often oxygen ends up being missing and the fire dies. Okay, but when these 3 are present in abundance, the fire propagates, and it may propagate extremely rapidly. Sometimes almost explosively, but it's not truly explosive. So when we sit there and we look at a fire burning, what we're watching is this vigorous oxidation of fuel in front of us. But there's something which you look at it and you say, what is burning? Or you say, oh yes, the wood is burning. Oh, how is the wood burning? It's actually a complicated process, because believe it or not, the wood that you see burning in front of you has to be heated to such an extent that the molecules that compose the wood actually evaporate, because it is fuel vapor that burns. It is not the solid fuel that burns. We've got to heat the solid fuel enough by heat of combustion around it that it begins to actually vaporize. And what we see burning as the flame in front of us is the vapors heated up to such an extent that they start to glow. And they actually, those burning vapors release a tremendous amount of heat, How it is passed on, we'll hear in a while. So flame is actually gas or vapor, which has been heated up so much that it becomes luminous. Its molecules actually start to produce light. The origin of the fuel can be virtually anything which is carbon rich, especially a liquid like a liquid fuel, or a solid like wood, or even gas itself. But obviously the gas does not have to then be converted to a vapor form. But when we pipe gas, household gas, which is methane, into our homes, and we burn it on the stove or we burn it in our heaters, that is exactly the same thing. We're combining a vapor, a gas, with oxygen. In the case of liquids and of solids like wood, they actually have to be heated to such an extent that they are able, that the vapor is able to be produced and the vapor reaches its ignition point. So there's an important, especially in dealing with fire, in a enclosed setting like home or whatever, there's one very important concept that we have to understand. And that is referred to as the flash point. And that is the lowest temperature at which a substance gives off enough vapor that it can be ignited. Remember, we need enough fuel. We need enough vapor combined with oxygen for it to ignite and start burning and releasing heat of combustion. The lowest temperature at which a substance will release enough vapor to ignite is called the flash point. And different substances have very, very different flash points. So for example, something like gasoline has an extremely low flash point. It's minus 50 degrees Fahrenheit. What this means is that even at minus 50 degrees Fahrenheit, gasoline will release enough vapor that it can ignite if we put a flame to it. It doesn't mean to say it catches a light spontaneously at minus 50. What it means is minus 50, it releases enough vapor that if we set it alight, it will burn. Below minus 50, it doesn't release enough vapor to be ignited. Other substances have a much, much higher vapor point. Wood, for example, would be hundreds and hundreds of degrees above freezing before it was sufficiently hot that it would release vapors. But it does. That's why wood burns. The temperature at which the substance will actually ignite, that is something completely different. This is the ignition temperature that we talked about before. And here, for example, here are a few of the fuels, the liquids, which will easily catch a light. Remember, with gasoline, such a low flash point, at a higher temperature, normal room temperatures and everything, it releases abundant vapor. And it has a flash point. These look very high. They go all the way from like 488 up to 869 for acetone. Fuel oil and gasoline are kind of in the middle here, in 500 degrees Fahrenheit. That looks very high, but it's actually not. That is easily accomplished in a spark or something like that. It is not, I should add, it is not accomplished by a glowing ember, such as the end of a cigarette. And all of those scenes in TV that you've seen where somebody pours gasoline all over the place and then tosses a cigarette into it and goes like that. That's nonsense. Okay, if you toss a cigarette like that into gasoline, all that will happen is that the gasoline will extinguish the cigarette, because that is not up in this region. It has not at the ignition temperature. However, if you were to toss a lighted match in, a burning match, the match is burning. You can see it burning because it's the vaporizing and the vapors are glowing. That is much higher than this. And when you touch a burning match to gasoline, you're way over the ignition temperature and the gasoline will go. So obviously we need the temperature to be high enough for vapors to be produced. And then we need to put in a certain amount of starting temperature and ignition. And then once that happens, enough heat of combustion is released so that the fire propagates. The reaction, the oxidation reaction, propagates itself. And the process whereby, for example, something like wood breaks down under heat and starts to turn to vapor is called pyrolysis. And this is literally turning to fire. Pyrolysis, and it's the breaking down of molecules. Pyro, heat, and lysis means breaking. It's breaking down by heat. And when we look at a fire burning, what we're seeing is the wood vapor, is wood turning to vapor and oxidizing with the oxygen in the atmosphere. And the reaction is so vigorous, so exothermic. It is releasing so much heat that the gas begins to glow. The gas actually, the molecules are excited to such an extent by the heat, they begin to release light. And that's our cheery wood fire. Here it is burning, and you can see flame all over the place. But now what about the fire that doesn't produce flame? That lovely thing of looking at the coals, like when you're doing a barbecue or whatever. And in actual fact, this situation arises when there's the amount of fuel and the amount of vapor that's being produced has been drastically reduced. Because remember, what we're looking at is in fact glowing vapor. When we see a flame, when we see that red color, what we're seeing is glowing vapor. So in coals like this, they are coals, they are very much alight, but they are releasing very, very little vapor, and it's immediately around the fuel source itself. It's a thin, thin layer of luminous gas around the coal itself. So we've got now a fire going, and you will realize that you try to put your hand anywhere near a fire, the amount of heat it produces is enormous. And the reason for that is that things like wood or any sorts of fuel consist of carbon molecules which are joined together. And those carbon molecules have all been joined together. There's a tremendous amount of energy has been put into those chemical bonds. They are very strong bonds, and they contain a lot of chemical energy. When we pyrolyze the substance, we break those bonds. We break the bonds between, and we reduce it from a solid into small molecules of gas, which is what we are watching catch alight. That produces a huge amount. It releases all of that energy from the chemical bonds. It releases that energy as heat and as light. But that heat and light the heat we're going to talk about especially, does not just stay there. Obviously the light is radiated out, we see it, but the heat itself is also radiated out and can be transferred away from the source of the heat. And we know that because we sit in front of a fire to keep warm. And what is happening is we are receiving heat, which is being radiated out to us. It's energy that is being transmitted to us in the form actually of electromagnetic waves. It is being transferred to, we are picking it up as, in fact, in the infrared spectrum of the electromagnetic wavelength spectrum. So that much of the heat will be radiated out from the heat source. But heat can also be conducted. It can be picked up by a substance and it can be transferred. A good example of this would be if you would, for example, were to imagine holding a metal rod in a fire. Well, what happens is the end of the metal rod gets heated up tremendously by the fire, but then that heated metal begins to heat the metal next to it. And it heats the metal next to it, and it heats the metal next, and before long, you can't hold, even though you may be quite a way away from the fire. If you've stuck a metal pole in, pretty soon you can't hold the pole because it gets too hot. The heat has been transferred along the pole by conduction. What actually happens is that the molecules, the heat begins to excite the molecules. They begin to move faster and faster and faster. And when they move faster and faster and faster, they bash up against the neighboring molecules and they get them excited and they get the ones next to them excited, et cetera, et cetera, et cetera. This is heating by conduction. Just imagine a pot, a metal pot on the flame, and you try to pick up the pot and the handle is hot, not because it's been in the flame, but because this part of the metal pot was in the flame. The heat has been conducted to the handle. The next really important way in which, in terms of fire in a situation like a house or whatever, the other way in which heat gets transferred is by convection. Convection requires the presence of a convecting substance. So, for instance, water or gas, which is in the presence of a heat source. When it is heated, it expands. And when it expands, it becomes less dense and it will begin to rise. It's still heated. And as it rises, it carries heat away with it. It carries the heat. So it transfers the heat from one place to another by changing the physical properties of the convecting substance. Easy to imagine. If you have this pot full of water and you're heating it up on a fire, it's not, this layer here doesn't just stay hot and the rest stay cold. What happens is that the water here at the bottom heats up, it expands, and it begins to rise. And it rises up to the top of the pot. It may then cool and spread out and begin to sink again, but more is being generated here and is rising continuously. It's effectively stirring the substance. It's distributing, and this is what happens with convection, is it begins to distribute the heat away from the source and into the environment. And it may transfer, as we'll see in a while, a huge amount of heat, and a lot of damage may be done by heat conducted away from a single heat source. All of these three things, conduction, radiation, and convection, are extremely important in the propagation of fire, especially in a situation like, for example, a wildfire, a fire in a home, or things like this. When we use fire, then we control these aspects to ensure that the fire stays under control in a controlled situation. So when a suspicious fire or a fire of unknown origin occurs, an arson investigator arriving there will begin to investigate as soon as possible. There are two things that happen to damage a fire scene very rapidly. The first is the fire or the explosion. It does immediate damage. The second thing that damages a scene like that is the effort to actually put out the fire, because a tremendous amount of evidence may just simply be washed away by the fire hoses and everything else. Then a slow process of loss begins to take place, because a lot of the evidence at the scene may be extremely fragile. It may blow away. It may be destroyed very easily by falling material, etc., etc. The arson investigator needs to get there as quickly as possible and identify evidence for collection as fast as possible. Almost more than anyone else, arson investigators depend very heavily on photography and videography to gather evidence at a fire scene, because the scene, even if the fire has been put out, the scene may change very rapidly. When you imagine, for example, a burned house, all of the shelter aspect of the house is removed. And suddenly the whole scene is open to the environment, open to the wind, open to the rain, etc. So it's essential to gather the evidence as quickly as possible. There's one thing in arson, which is common to many scenes of arson, which operates in the arson investigator's favor. And that is that most arson is started with some kind of an accelerant, usually a petroleum-based accelerant, because gasoline is so easy to obtain, but maybe some other kind of fuel. A liquid fuel is usually used because a small amount of liquid fuel is extremely effective and can do a huge amount of damage. You can start a big fire with a small amount of liquid fuel. And the advantage that the arsonist, the arson investigator has is that the accelerant is very seldom consumed entirely. What happens with an accelerant like gasoline is it gets, say, an arsonist pours it all over a scene and then goes a distance away, throws in a match to start it. The fire may burn extremely violently, extremely rapidly, but the gasoline is very easily soaked up by things like wood, carpeting, these sort of things. And remember what we said, in order for it to burn, it's got to have enough oxygen present. When it soaks into a carpet, when it soaks deep into wood, it's very likely that gasoline is actually going to be preserved in small amounts, but plenty enough to be discernible to analysis. So that is one advantage that the arson investigator has. And one of the first things that they will begin looking for are sources of accelerant and places where that accelerant has been laid down. The first thing an arson investigator does is look for the origin of the fire. And there are certain signs that point to a particular place being an origin, being the point of origin. And these are often burn and smoke marks, which actually point to a place where the fire has begun. There may be several. An arsonist may set fire in several places, so several points of origin may need to be identified, but they are often identifiable unless the fire has utterly consumed the scene completely. And one of the important reasons for doing that is that very often arsonists will abandon the means of setting a light there close to the scene, or even something, they'll strike a match and throw it into the fire. They may drop the box of matches if need be. They may make an igniter, a delayed igniter. It can be done with a cigarette and matches, for example. It's commonly done. If you watch the movie, that was what that guy did. These things are traceable as long as they haven't been completely consumed by the fire. So these are typical burn marks here. which have resulted from somebody pouring an accelerant over a surface, over a floor. And you can see there are large areas here which are unburned, and the burn mark here marks the pattern of the accelerant. It burns, in this case, so rapidly that it actually has not set alight to neighboring areas. There are certain things which are commonly done at arson scenes, and that is that you will see a burn patch like this, where a fire has been started, and it'll be connected to other burn patches by streams of gasoline that lead from one to the other. So the arsonist feels that they can start a fire in one place, and then it will rapidly spread while the arsonist, of course, is hightailing it out of there. These burn patches are typically these irregularly shaped burns, and very characteristically, they often leave patches unburned in between. So remember what that we said about how fire is conducted and radiated, and how it can move by convection. These all operate at fire scenes. So, for example, here is a home which is on fire. But what has happened is that it actually started with a fire down here somewhere else in the bottom stories. So we've got to ask ourselves, well, how does the fire end up here in the upper stories here? And one of the most important ways in which this happens is by convection. This fire down here in the lower stories actually produces a huge amount of heat, and it can superheat air and get it moving. And as the air moves, it will carry with it all of that heat to another location. And it may carry sufficient heat that it can actually set alight to another area, even in the absence of flame. It can actually carry enough heat that it will itself be able to ignite fuels in another area. And that is exactly what is happening here. The heat is being conducted is being convected upwards to the upper levels of the house and setting it alight. This also leads to one important thing, and that is very often at a fire scene, an investigator can see where a fire starts because of characteristic burn marks here, which have also arisen because of convection. The gases have been heated here, have drifted up, and have been able to set alight, and it produces this characteristic V shape, which also points right to the place where a fire started. Okay, so I'm going to stop there, and we'll continue this then on Friday.